So after having computed the scene graph, the next thing to do in large-scale 3D reconstruction would be the structure for motion to get the sparse 3D reconstruction. In general, there are three paradigms of structure for motion: the incremental structure for motion, global structure for motion, as well as the hierarchical structure for motion. We'll look at incremental structure for motion in more detail, and I will just briefly go through global and hierarchical structure for motion in this lecture. As the name implies, it does structure for motion in an incremental way. First, we will choose from the scene graph any two views where the translation is a non-zero translation. This means that we omit any two views with pure rotation, and this can be computed or obtained from the two-view geometry that we use to compute the scene graph. And there are many pairs of images in the scene graph that might fulfill this criteria over here, the first criteria over here. And the best choice out of all these possible choices would be the one that has the highest inlier count. And the reason is because we learned in the earlier lecture that the computation of our fundamental matrix and all the essential is essentially a least square computation. And a least square computation would be much more accurate when we have more observations from the correspondences. Hence, we will want to choose the initial pair, which we also call the seed pair of images, to do our incremental structure for motion as the one with the highest inlier count. So after we have chosen this seed pair, the next thing to do would be to use the 8-point algorithm to compute the fundamental matrix or the essential matrix for non-planar scene. Alternatively, we can also use the 4-point algorithm to compute the homography for planar scene. And in both cases, we can use the fundamental matrix, essential matrix, or the homography to decompose it into the camera matrices for this first two view. We'll also set the scale to 1. What this means is that after computing the fundamental matrix, or especially the essential matrix, which you can decompose to the rotation and translation, we'll simply set the scale of the translation to 1. And in the case of the fundamental matrix, well, we recall that from the lecture of fundamental matrix, the fundamental matrix can be decomposed into two camera projection matrices P and P prime, where we will simply set this P prime to a scale of 1. And the next step, after we have obtained this P and P prime, the two camera projection matrices of the seed views, then we will do a triangulation based on the inlier correspondences from RANSAC, from the robust estimation of the fundamental matrix, essential matrix, or the homography. And we'll do this using the linear triangulation algorithm that we have seen earlier on to get the 3D points. So for these two views, for example, x1j in the first view, and we'll use I and j to denote the view index as well as the point index. And in the second view, it will be the correspondence of xij would be x2j. And we'll make use of these image correspondences as well as the two camera projection matrices to do a linear triangulation to get the 3D point xj. And once we have done this, we will apply the bundle adjustment. We will talk about the detail later to refine the camera matrices as well as the 3D points by minimizing the reprojection errors. And subsequently, after we have this first two view and the reconstructed 3D points, we will subsequently add more views into the reconstruction. And this is also why this method or this paradigm of structure for motion is called incremental structure for motion, because we start off from a two view seed views over here, and then we incrementally add on new views into the reconstruction. So an example here would be we start off with P1, P2, and then we reconstruct all these 3D points with the seed views of P1, P2, and we'll do image correspondences for P3, which is linked to P2 in the scene graph. So for example, let's say if I choose this as my seed view, and this is my P1 and this is my P2. So I will choose from P2 over here all the other possible pairs from those that link to P2, for example. So suppose that I chose this view over here because it's linked to P2, and this I would call P3 to add on to the structure from motion pipeline. And now P3, once I decided P3 from the third view from the scene graph, the next thing that I would do would be to establish the 2D correspondences. So 2D correspondences, and this is done by the image correspondences. So I can extract the sieve feature from here, for example, and then I will establish these correspondences from P3 to P2. And once I have established the 2D to 2D correspondences, I can see that from this correspondence, for example, I know that these 2 points are a correspondence from the 2D to 2D correspondence, and I know that the corresponding point in the second view is used to reconstruct this particular 3D point over here. So from this relation, I'll be able to establish the 2D to 3D correspondence over here. And uh, by doing this for all the other 2D image features on P3 to P2, I'll be able to establish a set of 2D to 3D correspondences from P3 to the existing 3D point in the scene. So once we have established the 2D to 3D correspondence, we can use the PMP algorithm to compute P3, the pose of the third image, with respect to the 3D scene. And this would be with respect to the world frame as well, since we are expressing all the 3D coordinates of the points with respect to a 3D world frame. And once we have done this, the next thing that we can do would be to establish more correspondences, other correspondences between P2 and P3, such that we can do linear triangulation on these point correspondences between P2 and P3. Since P3 now is already computed by the PMP algorithm, we can use it to do a linear triangulation of additional points and add it to the scene. And we can do this for subsequent views, for example, a fourth view where we establish the 2D correspondence first and use it to establish the 2D 3D correspondence to compute P4 using the PMP algorithm. Similarly, we can find additional correspondences between P3 and P4 and do linear triangulation to get more points. And we do this for many other views until we complete every image in the scene graph. Now, once we get the initial reconstruction from the two views, fundamental matrix, essential matrix, or homography, as well as a PMP to add in more views in the incremental structure for motion. Finally, we can do a refinement, a nonlinear refinement in the multi-view setting on over the multi-view camera poses as well as the 3D structures with what we call the bundle adjustment. So essentially what this means is that we are going to minimize the reprojection error. So for every single camera pose, we are going to project the 3D points that is seen in that particular image and minimize its error with the corresponding observation of the point in that particular view over the camera matrices as well as the 3D points. We'll talk about this in more detail in the next few slides. The second paradigm of structure for motion would be the global structure for motion. And what this means is that the first step here, we will make use of still make use of the scene graph, but the question can be posed in this way. For every edge in the scene graph, we will compute the relative pose, which is represented by R and T. So these are all the relative poses between every pair of images that is linked by the scene graph edges. And here we can easily compute these relative poses from either the fundamental matrix or the essential matrix or the homography, and depending on whether this is a two view. So in the usual case, we wouldn't use homography because most of the scene in the 3D worlds are non-planar. So the homography can only be applied to planar scenes. And a preferred choice or much more accurate choice is actually the essential matrix when the camera is calibrated, because we wouldn't have projective ambiguity here. So once we have computed all the relative transformation, which we can decompose from the essential matrix. So the essential matrix will give us R and T. So for every one of this pair of images in the scene graph, we can compute the relative transformation from the essential matrix to obtain this particular graph over here. So where each one of the nodes here represents a camera location. So there is an absolute location at each one of the point here. And now what we are given here, the edges, the relative pose, the R and T between each one of the nodes here. So this, let's say if I were to denote this as R1 and T1, for example, this would be the global pose of that particular camera with respect to a global frame, FW, for example. And this would be R2 T2, for example, and the relative edge over here would be denoted as R12 and T12 between the two views of 1 and 2. So similarly, we can denote this over here as R3 T3, the absolute pose with respect to the world frame, and the relative pose between these two views would be denoted as R23 and T23. So we'll do this for every single node in the graph to represent it as a absolute pose. Problem now becomes, given all the relative measurements, all the relative rotation and translation between every single pair of views in our scene graph, can we find a way to compute the absolute poses of all these camera poses in the scene graph? And the way to do this can be simply summarized as follows. We'll first estimate the global rotation by minimizing this cost function over here. So what we are trying to do here is that Ri and Rj here represents the global pose of any pair of images. For example, R1 and R2. So Ri, it's this guy over here, and Rj is this guy over here. And what we want to do here is that we want to minimize by computing the relative transformation, which is given by Ri and Rj transpose over here. We'll be able to compute the relative rotation between these two poses that is given by R12. And since R12 is what we observe over here, and these are the unknown global poses that we have to find out. In other words, what we want to do would be to minimize, to find out what are all the global poses such that when we formulate it in this way, when we compute the relative transformation between these two rotations over here, we'll be able to minimize its difference from what we observe, the relative transformation of the rotation between Ri and Rj. And in order to solve for this optimization, the first step that we need to do would be to convert the rotation matrix, which is a 3 by 3 matrix in the special octagonal group. In short, we denote this as SO3 group to omega, which is a vector of 3 dimension, such that the 3 by 3 rotation matrix is given by this formulation over here, exponential of the skew symmetric matrix. So this is a 3 by 3 skew symmetric matrix that is obtained from the omega over here, which is in the R3 space. And we call this the exponential map. That means that the mapping function that takes in omega and outputs R. And the inverse of this exponential map would be denoted as the logarithmic map that is given by the skew symmetric matrix over here. 3 by 3 matrix that's formed by the omega over here would be equals to the log of R. And so what more specifically, what we wish to do here is that given this rotation over here, which is a 3 by 3 matrix, we want to reformulate this cost function over here into the format of omega, where omega is just a vector of 3, so that we can actually do an optimization over the three parameters over here. So in other words, what we can do over here would be to simply compute the logarithmic map given Rij, for example. We want to compute the logarithmic map and convert it into omega. And similarly, for the unknowns Ri and Rj's and all the global rotations over here, we can put it into the logarithmic map to get omega. And more specifically, given a rotation matrix over here that looks like this, which is a 3 by 3 matrix, omega can be obtained from this equation over here. So after we have converted the rotation matrix into omega using the logarithmic map, we can rewrite this relation over here, Rij equals to Ri Rj transpose, into the linear equation in terms of omega over here, where omega ij, it's the equivalent of Rij after we put in the logarithmic map, and we get omega ij, which can also be written as omega j minus omega I. That is representing the relative transformation between the two global rotations over here. And what we can do here is that we can rewrite this particular omega j and omega I into this linear form over here, where omega global is simply a vector of omega 1, omega 2, and all the way until omega n, where n here denotes the number of global poses in the scene graph. And Aij would be simply made up of all the identity matrices, where it would be identity if it corresponds to that selection of that particular pose in that location. Otherwise, it would be zero. And then now this particular minimization function over here of Rij can be solved as a least square problem because we have simply reformulated it into this linear homogeneous system of equation, and it could be rewritten as A omega global equals to omega relative over here. This is omega relative, where A and omega relative are simply made up of stacking multiple of these equations together, all the equations, all the relative poses together. So every Rij over here will give us one equation over here, and we can do this for every single edge that we have in our scene graph. And by stacking all these equations together, we'll get A omega global equals to omega relative. Now, the unknowns over here would be omega global, which we can solve for it using uh, linearly square algorithm. And once we have computed omega global, we can convert it back into the rotation matrix by using the inverse of the logarithmic map, which is the exponential map as shown in this equation over here. So similarly, we can solve for the global translations using similar methods. But one complication over here is that the scale between every relative translation is unknown. So we can formulate it as Tij, which is the relative translation between any two views. Let's call this Ti and this Tj over here. So the relative translation over here would be Tij. And this is all computed up to a scale. And we will normalize that scale to 1 by simply, after we compute T from the essential matrix, for example, we will simply normalize this observation to be equals to 1. And now we want to make sure that the difference between the observed Tij over here, it's minimized with respect to the relative transformation that is computed from global post Ti and Tj over here. So we can formalize this as Ti minus Tj, and taking the difference between this and Tij that is observed from the computation of the essential matrix. And of course, we have to also normalize this particular Ti j over here. And we'll follow the same method as before, and what we have seen earlier on in our rotation matrix, which we can cast this into a least square problem of ax equals to b, and we will solve for x, which consists of all the unknown global translations. Then after we have gotten all the global poses from in the scene graph, the next thing that we can do would be to compute the 3D scene points using the linear triangulation algorithm with the image correspondences as well as all the global poses that we have obtained from our global structure for motion technique that was described earlier on. And once we have obtained all the camera poses as well as the 3D points, we can apply bundle adjustment to refine the 3D reconstruction. More detail of bundle adjustment will be discussed. And the third paradigm which we will look at would be the hierarchical structure for motion. I'll very briefly go through this technique in today's lecture. And the first thing that we will do here would be from the scene graph, we will do hierarchical clustering to get clusters of the scenes that are closely related to each other. So each one of these cluster could be seen as a connected component which are closely related to each other. We'll apply hierarchical clustering where the edges here will be weighted by the number of inliers between a pair of images that is computed from the robust two-view geometry that we have discussed earlier on. And once we get all these clusters in hierarchical structure for motion, the next thing that we will do is that we will do incremental structure for motion on each one of these cluster independently. So here is an illustration where this cluster we will apply incremental structure for motion to get a certain view of this as well as to get the camera poses with respect to a world frame, which we call FW1 over here. And then the next step, we will do the similar approach on the next cluster over here. So all the 3D reconstruction as well as the camera poses would be with respect to another local world frame, which we call FW over here, and so on and so forth. Then finally, once we reconstructed all the 3D points and the camera poses of each respective cluster, the final step would be to merge all these clusters together to form a global 3D reconstruction. And this merging of the clusters together would be done using similarity transform. So this is similar to the absolute orientation algorithm that we have seen earlier on when we talk about the PMP problem, when we have all the 3D correspondences, which can be established from the 2D correspondences between clusters. We can apply the absolute orientation problem to get the rotation translation. And finally, we will just need one point correspondence to compute the scale, difference between the two clusters before we can merge them all into a single consistent 3D model that looks something like this here.